So here is your next problem. Where does the normal line to the parabola? So I just heard normal line. So this is where you find a derivative, but then you have to do an opposite reciprocal. So I'm just breaking the problem apart. At the point, intersect the parabola a second time. So first I need to find the normal line at this point, which we can do pretty easily. First we start off with finding the derivative. That is actually the original function, not y prime. To find the first derivative, the derivative of x is 1. The derivative of x squared is 2x. And we want to find the normal line at the point of 1 comma 0. So there's 1. And we get negative 1. So what did we just find? We found the slope of tangent line at x equal to 1. So the slope of the normal line at 1 would be the opposite reciprocal, positive 1. So let's go through and find the equation of the normal line completely. So y minus y1 is equal to m times x minus x1. My y1 is this point here. My slope was positive 1. That was my normal slope, times x minus x1. All right, so we get y is equal to x minus 1. But now they want to know, when does this intersect this curve a second time? We know that they're going to intersect at this point 1 comma 0, because anytime we do a tangent, which we did right here, the tangent line will intersect at the point 1 comma 0, both on the curve itself and on the equation of the tangent line. But a normal line does the same thing. You still are intersecting the curve at that point. So both of these intersect at 1 comma 0. We know that. They're asking for a second time. So anytime you want to find two curves intersect, you can solve both equations for y and set them equal to each other. You're essentially doing a substitution for y. So x minus x squared, I want that equal to x minus 1. And so I get, and I'm actually going to move everything to the right side so that my x squared is positive, minus 1. These x's cancel. I get x squared is equal to 1. X is equal to the square root of 1, but plus or minus. So really I get x equals positive 1 and x equals negative 1. They gave me this one, so that's not the answer. They want to know where it exists. The second time it happens is at x equal to negative 1, and the y value, I substitute negative 1 back into the original equation, not the derivative. And I get y is equal to negative 1 minus 1, which is negative 2. So where? The second time is at negative 1 comma negative 2, if I didn't make any arithmetic mistakes. The last question I'm going to deal with here, find an equation of the line perpendicular to the tangent to the curve at a point. This is really a review of the problem we just did, but more of a basic concept where you're not doing much more than just finding the line perpendicular. So to the tangent. Tangent means f primed of x. Perpendicular means opposite reciprocal. Equation of the line. I need two things. I need a slope and I need a point. Do we have a point? Yes. Here's my point. So that's a check. So this I have. Do I have a slope? No. That's what we're going to use the derivative for. So we get 3x squared minus 3. We're trying to find the derivative at 2, the point. The 3 is the point on the curve. The derivative, you're only substituting in the 2. So you get 12 minus 3, which makes 9. So this is the slope of the curve at the point 2 comma 3. Find the equation of the line perpendicular. Well, this is the slope of the tangent line, therefore the slope of the perpendicular line. It's going to be the opposite reciprocal. Therefore, the equation of the perpendicular line, we're going to use our point slope form. There's the basic form. Put the point in. Negative, or y minus 3 is equal to negative 1/9 times x minus 2. And you can leave it like that unless otherwise specified. Hopefully the two videos together will get you kind of understanding how to do your applications. I know in class we haven't had that much time to go over and review all of your homeworks. So remember that I did say for 3.3, you're going to be mostly doing your rules. I'm only going to put a few application problems towards the bottom. And we will continue doing more application problems, okay? Enjoy!